So this is another truss problem. We are given this truss system and we're asked to find the forces and whether they're in tension or compression in each of the members. What I like to do first, and there's a pin at A and then a roller at D. And there are two external forces on it, the 3 kilonewton and 6 kilonewton forces. I like to first take a look at it and just decide on my approach. So first, look by inspection and see if there are any zero force members. I don't see any here, so no zero force members. And then the next thing I do is look to see if there are any joints where there are only two unknowns. So joint A, that's a pin, so there would be an X and a Y component, so there'd be four unknowns there. Joint E, there are four unknowns. Joint B, there are three unknowns. Joint C, three unknowns. And joint D, there are three unknowns. So we can't go straight into the method of joints. So first we'll need to solve for either the roller at D or A. So we're basically just going to do a free body diagram of the whole system. Since I'm on my tablet, I'm just going to copy and paste this and draw the free body diagram from that. So basically for the free body diagram, I get rid of the supports, and then I draw the reaction forces for this support. So a pin will have an AX and an AY. And then for a roller, we'll have the normal force to that surface, so ND. And so we can then solve for what happens at A and D. And I'm just going to do a quick, take a look and see what my approach can be. So basically, if I solve for ND just using static equilibrium, then I could go to joint D and I could solve for DE and CD. Then I could just move along, go to joint C, and then solve CE and BC. And then I could go to joint B and solve for BE and AB. Then I could go up to joint E and solve for AE. So if I do that method, I don't actually need to solve what happens or solve for the reaction forces AX and AY. So it'll just save you one little step. But see how you can just figure out your approach like that. So I'm going to start with the static equilibrium of the whole system, and I want to solve for that ND. So I'm going to sum the moments about A equals 0, and doing out of the board as being positive. And so this 3 kilonewton force is going to create a negative moment, so minus 3 kilonewtons times 4 meters. And then minus, and then go over to that 6 kilonewton one, 6 kilonewtons times 8 meters. And then plus, so create a positive moment, ND times 12 meters. And those are all the external forces that equal 0. So now I can solve for ND equals ND equals 5 kilonewtons. And it's pointed up. So we got that. So now we can go to joint D and solve for DE and CD. So joint D, we have D, we've got ND, and then we have CD, and we have DE. DE is going to need to be pointed down to counteract that ND, and then CD will need to be pointed to the left to counteract that DE. And the DE, let's see, it's going to be, so E is going to be, at the center here. So it's 6 meters to the right and 6 meters up. So that just means this is a 45-degree angle. Or it goes up and over 1, and then square root of 2 would be the think if we want to use common triangles, which I always like to use. So now we can sum the forces in the y direction equals 0, and we'll get negative 1 over the square root of 2 times dE plus nd. And so dE is going to equal the square root of 2 times nd, which is the 5 kilonewtons. And we get it to be positive, so that means we picked in the right direction, so that means it actually is in compression. And so dE is 5 times the square root of 2. That comes out to 7.07 kilonewtons in compression. And then we can solve for CD. If we sum the forces in the x direction equals 0, and we'll get, we have the x component of that dE, so that would be 1 over the square root of 2, and dE was also 5 times the square root of 2, or 7.07, and that's in the positive x direction, and then minus CD in the negative x direction equals 0, so these cancel out, so CD equals 5 kilonewtons. I picked the right direction, so it is indeed in tension. So there we go. So now we have CD and DE. So now our plan was to next go to joint C, and then we can solve for CE and BC. So joint C, so we have CD, which is in tension, so it was 5 kilonewtons. Then we have CE, and then we have BC also. And we have the 6 kilonewton force going down. So if we sum the forces in the y direction equals 0, CE, we need to know what direction that's pointed in. So CE, it goes 2 meters over and 6 meters up. So that equivalent triangle would be 1 and then 3. So 1 over 3 up, 1 over 3 up, and then the square root of 3 squared plus 1 squared. So square root of 10 would be the common triangle. Alternatively, you could find the angle there. But so sum of the forces in the y direction equals 0. So we get 3 over the square root of 10 times CE minus 6 kilonewtons equals 0. So CE equals 6 square root of 10 over 3, which that would equal 2 times the square root of 10. That equals square root of 10 times 2, 6.32 kilonewtons, and CE is indeed in tension. So now I have CE, and then we can also sum the forces in the x direction to get BC, so that's negative BC plus 5 kilonewtons, and then minus that x component of CE. So the x component would be 1 over the square root of 10 times CE, and CE was 2 times the square root of 10. And so BC is going to equal 5 minus 2, so 3 kilonewtons, and that is indeed in tension. So you see now I have BC and CE, so BC and CE. So our plan for the next one is to go, let's pick a different color, go to joint B, and then now we can solve for BE and AB. So joint B, so we have BC, AB, we have that, I think it was 6 or 3 kilonewtons going down. And then we also have that BE, and that's that same over 1 up 3 square root of 10, or you could do the angle. So we know BC is in tension. I would guess that, let's see, BE is going to need to be pointed up and to the right to counteract that 3 kilonewton force. And then I would guess that AB is going to be pointed to the left. But we'll have to check to make sure, which is always the case. So BC is 3 kilonewtons. So let's sum the forces in the y direction equals 0. And I start with the y direction because I know that AB is all in the x direction. So it'll just give us one unknown in that equation. So it'll make it slightly simpler. But so sum of the forces in the y direction. So we get 3 over the square root of 10 times BE. That's that y component of BE. Then minus 3 kilonewtons. That equals 0. So BE equals 3 times the square root of 10 over 3. So it's the square root of 10. And that equals 3.16 kilonewtons. And we were right about it being in tension. So now I have BE. And then we can sum the forces in the x direction. That equals negative AB plus that x component of BE. So 1 over the square root of 10 times the square root of 10. And then plus, and then BC is 3 kilonewtons. And so we get AB equals 1 plus 3, so 4 kilonewtons. And it actually is in tension. So now we've solved for AB and BE, AB and BE, so we just have AE left. So now we can go up to joint E, and we can solve for that AE. So joint E, sorry for that noise, there are a lot of helicopters for some reason. But so for joint E, we're going to have, let's see, we'll have AE, we have BE, which was 3.16, or square root of 10, I'll just say square root of 10, and it was in tension. Then we have CE, and CE was 2 times square root of 10 in tension. What was that? Oh yeah, CE. Yeah, so CE was 2 square root of 10 kilonewtons in tension. And then we have DE. And DE was 2, let's see, 5 times the square root of 2 in compression. It was in compression, and that's DE. And then AE, we're not sure, but I'm going to guess that it's in compression, but we'll have to see when we solve for it. So it doesn't really matter which one we do because both have X and Y components. We do know a little bit about the directions. So let's see. This is, yeah, 1 square root of 2. And then this here was the down 6 and over 2, so down 3 and over 1, square root of 10. And same over here, down 3 and over 1, square root of 10. And then this was 1, 1, and square root of 2. So now we just need to sum the forces in the x direction or the y direction equal to 0, and we could do either. I think either will be just as easy or hard. Sum the forces in the x direction equals 0. We have that x component of AE, which will be 1 over the square root of 2 times AE. And then BE is in the negative x direction, so minus 1 over the square root of 10 BE, and BE was square root of 10. And then plus 1 over the square root of 10 times CE, which is 2 times the square root of 10. And then minus 1 over the square root of 2 times 5 times the square root of 2. That all equals 0. So these cancel out. So we get AE equals 1 minus 2 plus 5 all times the square root of 2. So AE equals 4 square root of 2, which that equals 5.66 kilonewtons. We get a positive, so that means we were correct that it actually is in compression. And I'll circle this. And go up, and so now we've got all of the forces within the truss system.